experiments, vacuum techniques, HV and UHV, analysis techniques, XRD, SEM, AFM, MPMS, PPMS. I hope all of you can remember what these expansions are. Clean room technique, thin film growth, photolithography, low temperature instrumentation and measurements. Computer skill, software development using MATLAB, Origin and LabVIEW, Fortran, etc. And coming to this, development of a novel nano-sized magnetic and thermal sensor, materials development for sensor design, VATOT fellowship for some of the achievements he has obtained. That VATOT, VATAT fellowship for outstanding postdoctoral research from China and India. He has worked in Max Planck Institute for Chemical Physics of Solids and Tata Institute of Fundamental Research from our India. He has done his postgraduate PhD work from condensed matter and material physics, and study and characterization of structural, electrical, and magnetic properties, novel superconductors. Of course, I am proud to say that he is a product of Vijaya College, Bangalore. So I welcome Dr. Naren to come on the online platform. Dr. Naren, please join us. Thank you for accepting our invitation.
Yeah, thanks a lot to Professor Nagaraju, or PN as we call him. Yeah, thanks a lot for this opportunity to talk here. And I will now share my screen and hopefully it will go well. Yeah. So do you see my screen now?
Yes. I think we have to say yes.
Yes, sir.
Oh, yes. So three more. And yeah. Okay, so again, thanks a lot for this opportunity to talk here and for the introduction. So this is what I'm going to talk about. I realize that my title sounds a bit too specific, but I promise that the details of this talk are accessible to most of the audience here. So this work is basically what I did during my postdoctoral work a few years ago at the Weizmann Institute of Science in Israel. However, I'm, as PN told us, I'm currently in a different place. I'm actually in the city called Eindhoven in the south of the Netherlands. And I just wanted to give a short introduction to Eindhoven because I feel it may be interesting to a lot of you. Mainly because Eindhoven is considered as one of the high-tech hubs of Europe, definitely of the Netherlands. In fact, it's been developed over several decades to become what is called the brain port region of Eindhoven. So they boast of having what is called the smartest square kilometer in the world. So by that, they mean that the ratio of number of patents to number of people in Eindhoven is the highest when compared to any other city in the world. So consequently, there are a lot of big companies. Even though Eindhoven originally started out around the giant company called Philips, now there are several other companies. And since there is a lot of support for startups, there are startups coming up every other day in the city. Also, it is home to a very good university, one of the best universities in Netherlands, called Technical University of Eindhoven. And there is a very good synergy between these companies, startups, and this university. So I would suggest that if people are looking at career paths abroad, they should definitely consider opportunities in Eindhoven, because there are a really large variety of possibilities here. However, for most people in the world and also in Netherlands, surprisingly, the only thing they know Eindhoven, or the only thing they're proud about regarding Eindhoven is their football team. So for completeness, I'm also just showing you that. In any case, so the work I am going to show you is something that was done in the Weizmann Institute of Science, that is in Israel. And it's in a small town called Rehovot. And here, Weizmann Institute is perhaps one of the biggest institutions in the town. And so the lab in which I worked in the Weizmann Institute has historically been interested in magnetic microscopy. So let me give a short introduction as to why they're interested in this. As you can imagine, there is a huge difference in bulk magnetic signal from a material and the microscopic magnetic structure. So for example, you pick up a simple piece of iron. If you measure the average magnetic signal coming from the whole piece of iron, you might often end up finding zero. So because it's not yet magnetized, and the internal domains all cancel out with one another. However, when you look at the microscopic signal, you definitely would see that it is divided into domains, and within each domain, the magnetic signal is substantial. So it is quite obvious that the microscopic structure is quite important, and a high resolution magnetometer, consequently, is also of great interest for the same reason, as I said, and not just in ferromagnetic systems, but in a large variety of systems. So if we just have to flash some names of fields, important fields, up and coming fields that find interest in such a sensor, I can speak about all these fields as being really, that all these fields would find such a sensor very useful. Now, about a magnetic sensor, I'll just go through some basic slides before introducing our work. So typically, how would we measure a magnetic field? A classical way of doing it is, for example, using the Hall effect. And this has been known for centuries now. That the Hall effect is based on the Lorentz force experienced by charge carriers. So for example, if you have a material through which you're sending current, and there's a magnetic field applied perpendicular to this current, it would result in a potential difference developing in the other perpendicular direction. And this can be used as a way to measure the number of charge carriers. On the other hand, it can also be used as a way to measure the magnetic field. And this Hall sensor is really all around us. For example, this is a chip which is actually a Hall sensor present in a lot of our mobile phones. And it would help us, for example, use our compass apps, which would give us our directions in terms of north and south. And this depends on the Earth's magnetic field. And so that was about measuring the macroscopic magnetic field, like the Earth's magnetic field. However, what I'm talking about is about microscopic fields. And the same concept can be shrunken down and made into a microscopic probe. So for example, this is actually an array of Hall sensors. This is again work done in the same lab in which the rest of the work is described. So this blob you see here is actually a sample of interest. It is deposited on an array of Hall sensors. So basically there is this current channel in the center, and then there are these probes. There are these terminals across which you can measure Hall voltage, and you can send a current through the center. And of course, you can apply a magnetic field and find the signal response of this sample to magnetic field, for example. So yeah, so this is again a field that has been around for some time. And such Hall sensors can be made quite small, actually. It can be as small as 1 micrometer for each sensor. And then the sensitivity of these Hall sensors can be quite good, actually, around in terms of magnetic field sensitivity. It can sense fields as small as 10 nanotesla. And so in comparison, the Earth's magnetic field is around 50 microtesla. So it can sense a factor of 1,000 smaller or even better sensitivity. You get much better sensitivity in a Hall sensor. So that was about one kind of sensor. However, you can have several such concepts of sensors. So this is a landscape map done in or represented in this paper shown here. And it along the y-axis, it has the sensor size. So the size of the sensor would also give us an idea of how close you can reach a sample, and how close you can reach a sample also tells you how much signal you can get out of the sample. So on the y-axis, you have sensor size or sample to sensor distance. And on the x-axis, you have magnetic field sensitivity. So this is how small a magnetic field you can sense using that. And then there is another axis here, which talks about magnetic moment sensitivity. So magnetic field sensitivity is about, is more of a, it's more useful in terms of a macroscopic field when you think about it in a certain way. However, if you want magnetic moment sensitivity, that is, you can think of a magnetic field as composed of electron spins, for example. And then if you want to sense these individual electron spins or groups of electron spins, how small a group can you sense? That gives the magnetic moment sensitivity. It is related to magnetic field sensitivity and the size of the sensor. So in such a landscape map, you can see that the Hall sensors actually occupy a very large range. So you can have quite small Hall sensors and with very good field sensitivity. But then when you think of moment sensitivity, it is not very good when compared to the other options. So it's something like 1,000 Bohr magneton or even higher. So a Bohr magneton, as you can imagine, one Bohr magneton can be roughly thought of as the magnetic field, a magnetic moment of a single electron. So that is about Hall sensors. But the best known or the most sensitive magnetic sensor available is what is known as a SQUID sensor. It's a superconductivity based sensor. I'll speak about it more later. But typical SQUID sensors are extremely sensitive. They are, as I said, the best, the magnetic sensors with the best field sensitivity. So when we speak of magnetic field sensitivity, the larger the sensor is, the better the sensitivity, because you can collect more flux line. So you can see that when the sensor is quite large, we get extremely good magnetic field sensitivities. On the other hand, we are not talking about macroscopic signals. We are talking more about microscopic signals. So there are also smaller SQUIDs, which say can be deposited on a very tiny chip. And these SQUIDs can then be used to scan on a surface. So these are also hence called scanning micro-SQUIDs. And these naturally tend to be smaller and have better moment sensitivity. So you can collect better microscopic structure out of that. However, there are other sensors. So there are force sensors, like these are just like AFM tips, which are magnetic. So which can then as you know, AFM tips can get even atomic resolution when you scan across a sample. So these are extremely sensitive sensors, the magnetic force microscopy sensors. And then there is another very interesting kind of sensor, which is which has come out more of recent. That is this is called diamond nitrogen vacancy sensor. So diamond tips are constructed with a certain composition such that they contain certain vacancies, and they are used in a very interesting way to sense magnetic fields. So they're also extremely sensitive sensors. However, I'm more interested in the green blob here, which talks about the sensors we have worked on. That is called what we call the SQUID-on-tip, and I'll explain why it is called that. As you see, the SQUID-on-tip is one of the most sensitive sensors in terms of moment sensitivity, and that record of the best sensitivity is being broken almost every other month in that lab. It was happening even as I was working, because we were developing the sensor. The sensor was still in its development phase, so every day we were getting some new results. So yeah, so now I'll be talking more about the SQUID-on-tip sensor. So before that, a quick introduction to what these sensors are made of. So these sensors, as I said, are made of SQUID devices. And what is a SQUID device? The SQUID, the word itself, is an acronym for Superconducting Quantum Interference Device. So it is, as I said, it's the best magnetic sensor available. In all ways, it is better than the Hall sensor. And it's a well-known device. actually. It exists for almost a century now, and it's commercialized to a large extent. For example, this is an SQUID. This is a SQUID magnetometer device, which is commercially available from Quantum Design. I used this during my PhD, and I'm sure you would have seen it in some labs. It is so well developed that it can almost be used as a black box, and just put a sample in, get results out. And a lot of work is done using taking such a device for granted. So SQUIDs are quite well known. So again, just in case people are not aware of superconductivity itself, here is a very quick introduction. Superconductivity is basically, it consists of two important aspects. When we take certain materials and cool them below a certain temperature, the electrical resistance goes to zero. So this is actually the classic measurement done by the discoverers themselves, where in mercury they saw this transition. And the electrical resistance actually goes to zero. People have checked that this number is much smaller than 10 to the minus 5 ohm. And firstly, there is a temperature below which that happens. And then it's also necessary that the current you're passing through that sensor is below a certain value. So you can't keep passing arbitrarily large currents and still keep getting zero resistance. And the reason for that is the second aspect of superconductors, that is the expulsion of magnetic flux. So these superconductors, or these materials, once in the superconducting state, expel all the magnetic flux lines that might be going through them. And this again, there is a limit to how much magnetic flux it can expel. And the maximum magnetic field it can expel is also known as HC, the critical field. So this is one of those classic experiments you would have seen all the time, where there's superconducting material which has been cooled to liquid nitrogen temperatures and made superconducting, and then the magnet can levitate on top of it. So yeah, so that is basically what the main aspects of superconductivity that's relevant for this talk. And using such superconductors, one can construct what is known as a superconducting quantum interference device, or a SQUID device. So basically, we take a superconducting loop, that is the ring of superconducting material. And then, So this ring, for example, has terminals through which we can send current in and place for the current to go out into an external circuit. And the most important thing here is that in the loop, there are two places where the superconductivity is weaker. So this could be, for example, a very tiny non-superconducting part, or it could also just be a much thinner superconducting part, so that the critical current there is much smaller than in the rest of the loop. And this results in a very interesting property, that is the critical current of this loop. Critical current is what I mentioned earlier. Critical current actually becomes periodic in the magnetic flux going through that loop. So if we apply a magnetic flux through such a loop, the critical current goes through these oscillations. And that itself is very interesting. But practically speaking, such oscillations immediately mean that we have a physical quantity which varies quite sharply with magnetic flux. And this variation can then be used as a sensor. And that is what a superconducting a SQUID device does. So as you see in such regions, the critical current changes quite sharply with the magnetic flux. So that's what is the property that's used to sense magnetic fields using SQUID. And these squids can actually be made quite small. So here is a squid which is about 10 microns or even smaller. So it is done using planar lithography techniques. And the spin sensitivity can be as small as 100 Bohr magneton in these planar devices. These can also be used to scan. And it is about 100 times larger than the typical moment of a single electron, but still quite sensitive. But then, as you can imagine, due to a planar geometry, the problem is about reaching very close to the sample to get more signal. So you can see from this cartoon that if you have a planar sensor, it becomes much harder to reach the surface of a sample, and typically samples have microstructure in it, and that is a built-in disadvantage of a planar sensor. On the other hand, if one can imagine a tip-like sensor, like an AFM tip, for example, it can actually reach much closer, like this cartoon was showing us. So the question is, can these squids be deposited on such tips? And that the answer is yes. And that was the work in the lab I worked in. So how do we do that? So here again, there is a bit of interdisciplinary work. So okay. So this is basically a tool that is used in genetic research, basically. So say one takes a quartz tube, a thin quartz tube, and then by heating it in a controlled way and pulling it, one can actually get two tips out of it. And these tips are typically used for genetic research like cloning, where the tips which become as small as say 25 nanometer in diameter, they can be used to pull out say cell organelles and then manipulate them and do things like cloning. This is actually a picture of the first cloned sheep. So that is actually a tool from genetic research, as I said. But the most important thing for us from such a tip is that the hole at the center. So the tube has a hole in the center, but when you pull it to as small as 25 nanometer, the hole still doesn't collapse. So you still have a ring with a hole in the center. And that is the property we use in making these sensors. So go to the next slide. Yeah. So say we take such a sensor, so such a tube, which is pulled to say such a diameter at the end, and then we put it in a thin film deposition system, and then deposit the superconductor of our choice. And this will, this superconductor of our choice depends on the temperature range in which we want to work on, because it has to become superconducting in that range. And there are certain other considerations, but we choose the superconductor, we deposit it once at a certain angle, then we rotate it, deposit again, then we do a third rotation and deposit at the apex. And then this is a SQUID device. So basically, when you look at it from below, you see something like this. You have this large superconducting lead, which is this. And we have this ring where we have these two weak links. In practice, it looks something like this. And the main thing here is that in between the two leads, there shouldn't be any shorts. So those are the kinds of optimizations that we need to do about this manufacturing process. But then if we get that right, we actually have a SQUID device right at the tip. And this can be as small as 30 to 40 nanometers in diameter. And then what do we do with such a sensor? We need to first calibrate it. By calibration, I will show a couple of slides, which has a bit of detail, but I think it might be interesting for somebody who is wondering how to use these devices. So basically, this is how it's a deposited SQUID sample looks like. So this holder itself goes into a depositor, and then once it's done, we take it out and put it into a system where we can measure it. So as I said, it's a superconducting device. It has to be cooled down. So one of the ways of cooling it down is using such a what is known as a refrigerator. This is actually a cryogen-free dilution refrigerator. That is the name. And for the purposes of understanding, it is a system which goes to lower and lower temperatures as you go further down in the device. So basically, at room temperature here, and at the bottom, it could be as small as 10 millikelvin. So in such a device, a refrigerator, we can introduce our SQUID sample, and then we also need to have a magnetic field. And once we have all that in place, we can measure it. So what does measuring mean? Again, it's a very simple circuit, but the details are only for those who find it interesting. We have a SQUID device here, which is right at the end, and then we have a circuit through which we can bias and measure the SQUID properties.
Dr. Naren,
yeah.
Dr. Naren, could you put on the camera, because it appears to be blank, it seems. Put on the camera there. Put on your camera.
Oh, okay.
Yes, okay, thank you.
Are you seeing it? Not yet, I guess. Are you seeing it now?
Yes.
Okay. Okay. So I hope my screen is also visible till now.
Yes, it was visible.
Okay.
Screen was visible, but not touch.
No problem. Okay. So the idea is we have this SQUID as part of a sensor. And then you can imagine there are instrumentation challenges here, because the SQUID has to be at very low temperatures. But the rest of the circuit does not need to be, and also cannot be, for several reasons. So the circuit is actually distributed all along the height of that whole refrigerator. But in any case, this is the SQUID device. And then, and then the electronics is distributed all along the length of it, even though it's a very simple circuit. It's basically a few resistances and a biasing voltage and some way of measuring the current. So that part is at room temperature, and the rest is distributed all along, as I said. And then what we measure is basically current versus voltage characteristics of this device. So we vary the current flowing through it and measure what voltage we get. So basically we should get 0 voltage until it's superconducting. And then once it crosses the superconducting threshold, there is a voltage that develops. So the curves from that circuit look something like this. And then this can be translated into a false color plot. We plot all 3 quantities in the same plot like this. And this must remind you of that oscillatory oscillatory curve I showed you earlier. Basically, it is the same curve, and we need to choose points along this kind of map, and then bias the squid at that map. At that point, you would decide that the squid is most sensitive. So ideally, say something around here. If we bias the squid around here, then you would see that for small changes, you see a large change in the critical current, and that would then be translated into a voltage which we measure. So another thing we have to find is points at which the noise from such a sensor is very low. So we can also measure the noise spectrum of these devices. And when you look at the noise spectrum, you can see that at some points, at certain frequencies, you get a very low noise. So this is also because at lower frequencies, the instrument puts in more noise. So at certain frequencies, you get a very good noise level. And at these points, we should preferentially choose these points with low noise and high sensitivity to measure whatever sample we have. So that is how we calibrate these devices. And then we can decide on how sensitive these are. So this is just a table of the different materials that were used at the time I was working there. So you can see that there are some devices made of, say, lead and indium, which are so sensitive that their spin sensitivity is much better than 1 Bohr magnetron. So in principle, if we can isolate a single spin, which is a challenge by itself, this device can actually detect it. So that was a cool achievement of these devices. And then now I'll just quickly show you some results using this device. And for such results, basically one needs what is known as a scanning microscope, which is basically a place where you can put a sample, which is, say, this chip carrier here, and then a place to put the SQUID device itself like this. And then the device, the SQUID scans across the sample. Basically, in reality, it looks something like this. And this is just a 3D model. And now I will show some results on the vortices in a superconductor. So again, quickly speaking, vortices in a superconductor are cubes of magnetic flux. If you take a superconductor and then apply a magnetic field, you expect the magnetic field is expelled. But then under certain conditions, superconductors, the material finds it in terms of energy better to have magnetic flux lines enter the superconductor in terms of these vortices, in the form of these vortices. And there's a huge field of research on magnetic vortices in superconductors. And so this lab also used to do such work in the past. And now we use that same device I described to study these vortices. So basically, this is a lead thin film, which is patterned in this form with these hourglass shaped structures. So the white part is actually lead and the black part is etched out. So now in this black part, when it's superconducting and you have a tiny magnetic field, you can see that the magnetic field actually enters the superconducting region in the form of these vortices. And then you can play around with that in several ways. For example, you apply less field, there are fewer vortices. you apply more and more field, and then you can have more and more vortices in that region. So these are all very quick scans. Actually, these scans can be performed in around 2 minutes or so, and within 2 minutes we get such a beautiful plot. And then what else can be done? So we have these vortices in a static magnetic field. Now what we can do is we can apply a current through this channel. And when we apply current, what happens is these vortices, which are actually pinned to a certain place, now can start moving because they feel a Lorentz force. There's a current and there's a magnetic field, and the vortices start feeling a Lorentz force and try to move in the perpendicular direction. And that can clearly be also seen. So for example, you apply a small current of 16 milliamp, the vortices are all shifted to one end. And then you can reduce the current, and then they relax back. You make it zero for a reason known as pinning in these materials. It does not exactly come back to the center, but you need to apply a bit more of negative current in the opposite direction, and then it comes to the center, and then you can move it to the other side. So basically you can play around with this field of view of the vortices by applying different currents. And then of course, we can continue and increase the current and see what happens. And then we can see these streaks happening where vortices start entering from one end and start flowing out on the other end. So basically the force on the vortex is way higher than the pinning force. So they start streaking across the field of view. So yeah, and then finally I'd like to show this video which was taken, which again shows how much can be done on the vortex state of this device. Basically, we can focus on one particular vortex and then vary the current, and then keep measuring scanning the device, and then when we put these images together, we can see that we can trace the trajectory of a single vortex. And this can then tell us more about the material as to how hard the vortex gets pinned to a certain region, and how the pinning force changes with the current, and so on. So a lot of work has been done on this, and there are references, as you see here, in which you can look, in which you can read up more details. But yeah, so this is one of the cool videos that were produced during my time in this lab. So yeah, now yeah. So anyway, so that was an introduction of SQUID-on-tip and its capabilities. And for more details, you can go to the website of this lab and look at more recent publications in which a lot of materials have been studied using these devices. So yeah, so now if you have any questions, I'm happy to take. Please don't hesitate to ask me to go back to a previous slide in case you want me to.
Okay, students, if you have any questions, please ask. I think we would be happy to answer your question. Yes, anybody? No question. Yes, yes. Yeah, you can stand and
speak loud or come this way.
Yeah.
No, I'll just tell the question. He was talking about the pinning thing, right?
No, you go to the mic. Come here. Yeah. Wait for a few minutes, Karen.
Okay. So, could you explain more about the pinning thing that you were talking about, where you had to apply a negative? Can you hear me? Sir, can you hear me?
Yeah.
Okay, so could you talk more about the pinning thing in the same slide that you were on?
Yeah.
Could you explain more about the pinning thing that you were talking about, where you apply an extra negative current so that it comes to the center of the?
Yeah, sure. So when these films are deposited, typically there are imperfections in the film, and there are certain regions which have maybe weaker superconductivity, which have crystal defects. They don't form as a single crystal, but there are defects in the single crystal. And these regions are energetically more favorable for a vortex to sit at. So these regions are called basically pinning centers of the vortices. And of course, they're dependent on the material. They're also dependent on how the material is deposited. And so then you need extra force. So there is a certain pinning force. You can quantify how much energetically favorable it is for a vortex to sit at a certain site by the pinning force. So basically, if you apply a certain current, you need to apply a certain current and create enough Lorentz force for the vortex to be moved out of a pinning center and then move to the next one. So basically that's what happens in this this experiment, where we apply a current as well to the static vortices. And you can see that the vortices start moving to one end. By that I mean they have enough force to jump from the original site to the next site and hold there. And then you can reduce the current and see what happens. You expect that they come back to an earlier state, because the vortices like to be distributed across the material, mainly because the vortices, you can think of them as current carrying loops, and they basically repel each other. So they would like to be distributed across, but it also, the counter force is also the pinning force. So it tries to relax, but because of pinning, they don't relax to the center at zero current. But then you need to apply a bit of negative current, and then they relax to the position which we would consider as a center position or equilibrium position, and or a zero field position rather. And then of course you can apply a current in the opposite direction, and the vortices start moving in the opposite direction. And another cool effect of the thing to notice in these pictures is that you see one side of the hourglass is actually bright and the other side is dark. And that is again basically the magnetic field along a current carrying line. So as you know, if you have a current flowing across along a conductor, you have a magnetic field which circles around the conductor. So say the magnetic field lines come out of the paper here and go into the paper here, or the screen here. And when you scan this field of view, you also see that you see more of a magnetic field here. So it's a bright region and dark region here. And then it flips when you change the current direction. So that's another nice fundamental physics kind of thing you can see in this experiment. But yeah, that was an aside. So pinning was whatever I said earlier in this.
Yeah, please come here if you are asking a question. No? Anybody else? Dr. Naren, again, could you tell them, because the students from different parts of the country, and some more opportunities abroad, could you tell them? Only about 3 to 4 minutes. You were not able to hear me? Yes, yes. In general.
Yeah, sure. So let's see how to put it. So for example, in my case, I did a PhD in TIFR, and then I was doing I decided, and that was in fundamental research. As you know, the name of the institute itself is Tata Institute of Fundamental Research. And then I worked in another institute in Germany and then in Israel. And then slowly I started doing work which is more applied. It is more device, like developing of a device and so on. So my interest also changed to looking at more applied research and devices and instrumentation. And then naturally I moved into industries where such instruments were being developed based on some physics research done somewhere. Like the first place I worked was a refrigeration industry, where we were basically making these kinds of refrigerators, which I just showed you here. So yeah, so we were actually making such refrigerators in that company. And now I'm working in a company where we make transmission electron microscopes. So it's a completely different field, but then a lot of instrumentation and such skills that I had developed during all this research also was relevant in this industry, and it's a new thing for me. So that's how I moved. But then this is one progression where you do something and slowly realize something and then move to something else. But of course, there are people who at the level of BSc or MSc already are aware of what their interests are. They might want to directly go into an industry or do a PhD in a particular field. So I think those are the directions in which one could start thinking at an earlier age, say at a level of bachelor's and master's. And then you could look at opportunities in for example, in Eindhoven. If we are talking about Eindhoven, the Technical University of Eindhoven has programs for master's students. There are programs which work closely with industries. So if you are interested in doing and moving to industries, that would be a very good program to get into, where you join a master's program in that university, and you are already closely working with the company, and then you have a lot of opportunities in other companies then. So maybe a good thing to think about is about the difference or what you feel about working in a company or working in academic research, because those two things can be quite different. And then that immediately makes you ask questions about how to go about it. And then if you feel strongly at the stage of masters, you can start looking at an industry position even at that stage. Or you could, of course, do a PhD. It's a very good skills building program. You can learn a lot, and during that time, you also have a lot of time to yourself where you can think and talk to experts, and you can consider changing after that. Or of course, you could also progress in the academic stream to say a university and so on. So yeah, so if you want to know more about any possibilities, say in the Netherlands or in Eindhoven, or in general, if you want to discuss, you can of course also contact me later. PN would have my contact details, so I'm happy to also talk to you.
Yeah, at least you have accepted our invitation and you have come on platform, and therefore again I am thanking you. Thank you again. Thank you. Thank you.
It was my pleasure. Thanks a lot. Yeah, have a nice conference further.
Okay. Thank you.
Bye.
Okay.